This is levitron, and it works on a very simple principle. This is a large magnet, this is a small magnet, and they repel each other. If this thing wouldn't spin, it would just flip and fall. But due to the spinning top magnet, it stays in equilibrium, in very subtle one.
Andrei Geim is one of the world's leading authorities on high-power magnets. What's interesting about magnets is the way they can create levitation.
There is a strong magnetic field here, but my hand doesn't disturb this magnetic field. If I use something else like magnetic iron scalper, it will just disturb magnetic field and the levitron will fall.
In vast laboratories in Europe, the USA and Japan, physicists are now experimenting with magnetic fields tens of thousands of times greater than that of the Earth.
All right, Tom, is it ramping up?
This equipment uses 20 megawatts, enough electricity to power a small town.
Really? Yeah, I can feel it. All right, ferromagnetism. Let's do some diamagnetism.
And all this energy goes into creating a magnetic field in an area just 2 inches across.
That's good. The magnet must be running warm. Okay, I'm going to lower the launcher now.
When subjected to magnetic forces of this scale, it's not just metals like iron which are affected. Almost any material can be magnetized.
Good. We have liftoff.
And when magnetized, it floats.
Magnetic levitation strikes one's fancy. It's a fun thing to do, and there's a lot of surprises. But going beyond just the fun, exciting aspects of it, there really are some things to learn. And one of the things to learn is the biological processes, either in plants or animals. How are those affected by gravity?
Space travel means long periods in zero gravity. And what's already been found is that most living things have problems in this environment.
Plants don't grow well in space. For some reason, a plant on the space shuttle, for instance, in a microgravity environment, doesn't do well. Now, of course, everybody's interested in Mars. We probably want to go there, but it's not an afternoon journey or a day journey. It takes a long time. And so we need to be able to grow our own food.
It will take 8 months to get to Mars. The plants space travelers will need for food have so far failed to thrive, though no one's yet sure why. Do they need some gravity for their roots to develop? It's an open question which these experiments should help solve.
It's very important to learn why plants do not do well in space and fix it, fix the problem.
We live on the Earth and we know that gravity influences us. The only way to find out what would happen without this gravity is to put different objects, chemical reactions, humans, and etc. in space. And it's rather costly and complicated process to find it out.
It's far cheaper to create microgravity in labs than do experiments in space. A simple experiment, which would cost hundreds of thousands of dollars in the shuttle, costs a 50th of that price in the magnetic lab. But at Andrei Geim's lab in the Netherlands, research has gone further than experiments with plants. Nijmegen was the first to do magnetic levitation on living creatures. The small bore of the levitating magnets has restricted research so far to small creatures like spiders and baby frogs. They seem to cope well with zero gravity in the short term. But what effect does it have on a living organism to be turned into a magnet, even briefly? Andregain believes the risks are small, because people seem to suffer no ill effects from the kind of powerful magnetic equipment used in modern medicine.
It's approximately the same magnetic field as the frog or spider experienced. And humans, as you know, they're the most sensitive instruments you can imagine. If humans do not feel anything, I'm sure the frog doesn't.
So if animals can be levitated in a magnetic field, who's going to be the first human volunteer?